One of the great challenges with electricity markets is that a mismatch between supply and demand, caused by, for example, the sudden loss of a generator, can very quickly cause other generators to trip off because they exceed their ratings, and ultimately we end up with that domino effect called cascade failure. A quick bit of technical background. Physical characteristic of the system which underpins this type of cascade failure is called system frequency. While the nature and mathematical background of frequency is covered in another video, in short, it represents the speed of the system, measured in cycles per second or hertz, which in turn is a result of the balance between the push of supply or generation and the pull of demand. Now, the way the New Zealand system is set up, a perfectly balanced supply and demand system gives us a frequency of 50 hertz, which means 50 cycles per second. The US, for example, is set up to be 60 hertz to be the balance point. Now, if demand equals supply, the system slows down, that is, frequency drops. A key point in the frequency decay is 49.25 Hz. This is defined under the code as an under-frequency event, and this is the point where we really need something substantial to respond in order to avoid cascade failure. Typically, we get failures on the system which cause frequency to go through this point about a dozen or so times a year. To prevent this, the system operator arranges for there to be standby reserves or instantaneous reserves to bring the system back into balance. The immediate priority is to stop or arrest the decay in frequency, and it does this through fast instantaneous reserves or FIR. These guys need to act within 6 seconds of the event occurring. But ultimately, to restore the balance in supply and demand, it does this through sustained instantaneous reserves or SIR, which needs to be up and running within 60 seconds and stay on for 15 minutes. Remember that under N-1 security, sufficient reserves must be procured at any one time to cover the loss of the biggest single generator operating on the system failing. The specific piece of plant which would result in the biggest loss of megawatts is sometimes said to set the risk. This could be usually a combined cycle gas turbine. But for the purposes of setting the risk, the HVDC is also treated as a generator in the receiving island and a load in the sending island. This means that the HVDC, if the flows are high enough, could also be setting the risk. The system operator needs to determine at all times both the risk in the system at any one time, in terms of which piece of kit is setting the risk, as well as figuring out how much of the fast 6-second reserve and slower 60-second reserve, the FIR and the SIR, is required. So the sensible thing to start this calculation is to figure out what the largest possible single failure is. To know that, I need to know what's running or what's dispatched on the system at any point in time. Then I can figure out whether it's a combined cycle gas turbine or the HVDC that is setting the risk. The calculation of what's required over the shorter 6-second time frame, the FIR, is complex. Remember that the purpose of the faster reserve FIR is to arrest the frequency decay. Here the system operator needs to predict how frequency will respond to the failure, taking into account all the governor response that's programmed into all the generators, and as well as the system inertia. However, in terms of figuring out SIR, the sustained response, this calculation is a bit more straightforward. Ultimately, by the time you get to 60 seconds after an event, you just basically need as many megawatts ramped up as you lost in the event. So now we have our required FIR and SIR. Think of it as the demand for reserve across the two products. But that's not the end of it. As we will see shortly, the requirement for FIR and SIR may change the way we dispatch the grid. Now, these complex calculations around predicting frequency decay following an event are performed in a model called the Reserve Management Tool, or RMT. It does this in every half hour. So, having set the demand for reserve, we now need to figure out who is going to provide it and how. Generally speaking, we need some piece of kit that can act really fast following the failure of something else. Broadly speaking, there are two things you can do once a generator or the HVDC has tripped. You can quickly increase generation, or you can quickly decrease demand. Increasing generation is also known as spinning reserve. In terms of demand, there's a fast-acting reduction known as interruptible load. This tends to be either ripple-controlled hot water cylinders or certain industrial processes that have relays that can sense the system frequency. As soon as they detect a certain decay in frequency, the relay acts and instantly trips off whatever process is using the electricity, thus achieving a reduction in demand. In terms of spinning up generation reserve, there are two options. The first is known as partially loaded spinning reserves, or PLSR, and the second is known as tailwater depressed spinning reserves, sometimes abbreviated to TWD. These are a bit more complex than just interruptible load, so we're going to take a closer look. Partially loaded spinning reserve, PLSR, is, as its name would imply, provided by a generating unit which is already partly loaded. It's already generating a certain amount of megawatts. That is, it's generating that prior to the event. The advantage here is that since it's spinning already, it can increase its output very quickly, which makes it ideal to provide the 6-second FIR. But the exact amount of FIR is actually quite complex because the amount of reserve a generator can provide depends on what level it's generating at just prior to the event. Specifically, there are 3 key constraints on partially loaded spinning reserve. These constraints describe how much the amount of reserve generation is available and how that relies on what generation level the unit is dispatched at prior to the event. So, firstly, at low levels of generation pre-event, the amount of extra output a generator can provide is usually a proportion of its output. This is represented in the chart by the upward sloping line that I've just shown on the screen. The slope of this line is referred to as the reserve angle and is communicated to the system operator. So as we move up our generation level pre-event, we can provide more reserve according to that straight line. Once the generator reaches a certain output, there is a maximum amount of reserve it can provide within 60 seconds. This is the horizontal line in the chart above, and that's just a function of the fact that there's only so much oomph that a generator can put into the system within 60 seconds. Finally, ultimately, there's an overall joint limit on the unit's capacity. Whether it be energy or reserve, a unit can only generate so many megawatts. So this is obviously represented by a negative slope line at 45 degrees. The generation plus the reserve must be less than or equal to the unit's capacity. The shape of this capability is often referred to as the inverted bathtub constraint. All 3 constraints must be communicated to the system operator so it can predict the exact response of any generator that is being dispatched as reserve. Now, while PLSR can be provided by a range of different generator types, tailwater depressed is special to hydro. The key difference between PLSR and tailwater depressed is with TWD, the unit is not actually generating anything prior to providing the reserve. So in a sense, it needs to fire up from a cold start, but that's not strictly true, as we will see. Now here's a schematic of a hydropower station. Take a minute to familiarise yourself with all the parts that are labelled, as this is going to get a little bit complex. Effectively what happens is that prior to any event, the station operator offering TWD holds the water back from hitting the turbine so that there's no water actually flowing through. It just sits in the penstocks, if you like. It does this by closing what are called wicket gates, which sit right next to the turbine like these ones there. When these wicket gates are completely shut, no water can flow through and hit the turbine. Now, while there's no water hitting the turbine, the generator above the turbine is actually used as a motor to spin the turbine. But it isn't generating anything, it's just spinning. In fact, it's consuming a little bit of power to turn it. Now, you may think this is a bit like a washing machine turning a generator in a big pile of water, and it would be, were it not for the fact that compressed air is pumped around the turbine so that it actually is spinning in air. This is how it's a bit better than just a cold start. Stay with me here. When a frequency event is detected, our wicket gates are opened. All the water that was pent up in the penstock now flows through the wicket gates onto the already spinning turbine, and it starts generating. At this point, there'll probably be quite a spectacular explosion of that big compressed air bubble out the tail race as that air is ejected. So there's a bit more of a delay in the unit ramping up compared to PLSR, as it has to wait for the wicket gates to open and the water to hit the turbine. These structures don't open instantly, but they can actually be quick enough that with sufficient water, it can, in some hydro stations, hit the turbine fast enough to provide some fur. Until now, we've mostly talked about what we call under-frequency events, where a source of supply like a generator trips off and the frequency falls. However, if a large enough load trips off, frequency can rapidly rise, which causes similar problems for generators connected to the system in terms of them staying within their design standards. Now, other than perhaps New Zealand aluminium smelters, it is unlikely that there are industrial customers that could cause this. However, remember that for the purposes of calculating the reserve risk, the HVDC is treated like a generator and receiving island, but also like a big load in the sending island. If the HVDC failed in the case illustrated on the screen here, as well as potentially leading to an under-frequency event in the North Island, it could also lead to a sudden oversupply of generation in the South Island, which would cause frequency to rise. Hence, we need our generation reserves to back off rather than quickly increase in that island. Of course, this is also possible in the North Island when the HVDC is flowing south. While this is less frequent, the system operator still contracts over-frequency reserves in both islands to cater for the event when the HVDC is flowing away from that island. So, in summary, there are two types of reserve required: FIR, which must react within 6 seconds and stop the frequency decay, and SIR, which is a more sustained response that brings the system back into balance. These requirements depend on what generation is currently dispatched, and this calculation around what effect they'll have on frequency is done by the system operator every half hour using the Reserve Management Tool, RMT. Instantaneous reserves can be provided by generation as tailwater depressed or partially loaded spinning reserves, or by demand customers as interruptible load. An overfrequency reserve is contracted in both islands to cater for the situation where the HVDC is exporting large amounts from that island.